This was a talk of Egor Gladin from Stochastic and MIPT. Egor, I see you here. Please start.
Hello, my name is Egor Gladin. The topic of the present talk is Vaidyas cutting plane method for stochastic optimization in small dimension. Consider a stochastic optimization problem on a compact convex set with non-empty interior, where the dimension n is relatively small, a few dozens. F is a continuous convex function, and unbiased stochastic oracle satisfies sub-Gaussian assumption for some sigma. Here's the sub-Gaussian assumption. Such problems are ubiquitous in machine learning and hence are highly relevant. Let us discuss the type of solution we are looking for. X tilde is called epsilon beta solution of a stochastic optimization problem, where epsilon is positive and beta is between 0 and 1. If the probability that the error is greater than epsilon does not exceed beta. This is the type of solution we are looking for. The talk is devoted to the method that achieves epsilon beta solution after these many iterations with batch size R, where the notation O tilde means the same as big O up to logarithmic factors. Thus, the method converges linearly and enables significant parallelization. To compare, the famous stochastic gradient descent requires the number of iterations that is inversely proportional to the epsilon squared, and batch parallelization doesn't work in the non-smooth case. Thus, stochastic gradient descent is better in terms of total number of subgradient evaluations, but the proposed method is significantly faster if it is possible to perform computations in parallel. Let's recall the notion of subgradient. The vector A is called a subgradient if this condition holds. In the univariate case, we can visualize it as a slope of a line that touches a graph of the function in a specified point and lies below the graph elsewhere. Thus, a non-smooth function can have multiple subgradients in a single point. The generalization of this notion is delta subgradient for non-negative delta, which has the identical condition with the added term minus delta. This term allows for some inaccuracy, which can again be visualized in the univariate case as a slope of a line that goes through the point gx minus delta and lies below the graph. If in the case of smooth functions we have single subgradient, we can have multiple delta subgradients, and this delta allows for some inaccuracy, and this notion will be used in the analysis. Now let us discuss Vaidyas method. It was proposed by Vaidya in late 80s as a method for minimizing a convex function over a compact convex set. It is a cutting plane method, which means that on each step we consider some set that contains a solution, and we cut out a part of the set, thus reducing its size and moving closer to a solution. In particular, the sets in Vaidyas method are defined by pairs A, B, where A is a matrix and B is a vector, and sets have this form. Cutting out a part of a set is done by adding a constraint to this system, which means adding a row to matrix A and element to matrix B. However, if there are too many constraints and it gets difficult to handle them, we remove the least useful, in a sense, constraint. I don't go into too much detail because the full description of the algorithm would take numerous slides. Well, originally, the new constraint is added based on the subgradient in the current point. But what if we use a delta subgradient instead? As it has been proved in our paper, the algorithm will preserve convergence. Moreover, the error will not accumulate from step to step, and it will appear as an additional term delta to the original linear convergence estimate. Such property will be very useful for us. Now let us introduce a stochastic oracle with minibatching, which is an average of R stochastic oracles called at the same point. The following lemma has been proved in our other work. If the stochastic oracle with minibatching, where each term satisfies sub-Gaussian property, was called n times, then for any beta between 0 and 1, each value returned by the oracle is a delta subgradient with probability at least 1 minus beta n, where delta depends on beta, batch size R, and constant sigma in this way. This lemma connects the notion of delta subgradient with the notion of stochastic oracle, and therefore justifies the use of Vaidya's cutting plane method with the stochastic oracle. This brings us to a theorem that states that Vaidya's cutting plane method with minibatching achieves linear convergence if the batch size is large enough. The complexity depends on the dimension of the problem n. Moreover, each iteration involves inversion of a square matrix of size n, which is why the dimension is assumed to be relatively small, say up to 100. The experiments are in progress right now, but I would like to share the results of the experiment from the previous work, which is based on the same ideas, but uses ellipsoid method instead of Vaidyas method. These are both cutting plane methods, and they have similar properties, but the complexity of ellipsoid method is proportional to the squared dimensionality, while the complexity of Vaidyas method is proportional to n times logarithm n. This fact raises expectations that Vaidyas method will perform even better. As far as the experiment on the slide is concerned, it was devoted to training a logistic regression model for a binary classification problem. The number of features equals 55, and the dataset size is approximately 500,000 examples. As we can see from the plot, the batch parallelization doesn't speed up the convergence of SGD, and the ellipsoid method achieves lower values of the objective. The conclusions are as follows. Vaidyas cutting plane method with minibatching can be used for convex stochastic optimization, but it requires that the dimension is small and the batch size is large. The method converges linearly with no requirement of smoothness or strong convexity of the objective, and it outperforms SGD if extensive parallelization is possible. Thank you for your attention, and I would also like to thank Alexander Gasnikov for contributing to the present work, as well as for hosting this session. If you have any questions, please feel free to ask.
Thank you, Igor. Please, questions?
One question.
Okay. Yes, yes.
Let's look at the first slide or second. Please, in the Formula 1, Xi, it is probable variable with which distribution? What is the distribution of Xi?
So it is a random variable, and the distribution. So what is important for us is these properties, and as long as the distribution satisfies these properties, we do not really care that much what is the distribution. It is important that the expectation of the function is a continuous convex function. It is important that the oracle is stochastic oracle is unbiased and satisfies this assumption. And as long as we have these properties, then the distribution is good for us.
And Xi may be random variable, uniform random, or normal variable. The results will be the same.
I guess so. The results. So the theoretical bounds they depend on the constant sigma, which depends on the random variable, and also the bounds depend on the range of values of the function f. So I can say that the results will be exactly the same for two different distributions, but for both distributions, we will have linear convergence if the batch size is appropriate, is large enough.
It is strange for me. Thank you.
Okay, thank you. Maybe more questions? Yes, thank you very much, Igor. Very nice talk, very nice English. It's, I guess you fulfill a great progress.